Hello everyone. So, this is the second lecture of week 3. So, you can recall that in the previous lecture we began with a motivation for optimization algorithms, and we gave a framework for how an optimization algorithm would work, right. So, you just will see it on the screen. So, this is the basic algorithm. You initialize a particular point, right. So, and in each iteration, okay, you choose a descent direction and the appropriate step size, right. So, like when you are traveling, someone actually tells you that you have to travel in this particular direction for such distance, right. So, in your Google map you can see that it says go straight for another 1.2 kilometers, right. So, what does it actually say? It actually gives you the direction and the step size, right. So, that is exactly what you are figuring out in each of the iterations, and you also have a stopping criterion, because at the last step you want to know that this is actually the last step, right. So, like at the end Google Map says that you have reached your destination, is not it. So, that confirmation actually occurs by del f of x k less than or equal to the tolerance. Okay. So, this is the basic framework for any optimization algorithm that we are going to see throughout this course. Okay. So, in various methods we will actually choose the descent direction and the step size. Okay. All right. So, let us actually now try to understand how to choose the descent direction and the step size. Okay. So, we will start with the step size. Okay. So, it's nice to say that you just have to choose the descent direction, just choose the descent direction and choose the step size. Okay. But you can recall that we saw in this particular example, when f was x1 squared plus x2 squared and x naught is 5 comma 4, we have so many directions to choose from, right. So, if you are given a particular problem and you say that choose one from an infinitude of directions, that is a very bad way of writing an algorithm, right. So, you must actually say that if this is f and this is x naught, choose this particular d, right. And in a similar way, recall that when you had f to be x1 squared plus x2 squared, x naught to be 5 comma 4 and d naught equal to minus 1 comma 1, what we said was alpha needs to be between alpha needs to be in the interval open 0 comma 1, right. That is again an infinitude of values, is not it. So, again this is not what I am looking for. What I am looking for is a specific value of alpha, say that you take this particular value of alpha, right. So, how do I choose the specific descent direction and the specific step size value, right. So, the choice of step size, okay, is given by a set of algorithms actually called as the line search algorithms. Okay. So, line search algorithms are algorithms that search for a step size alpha k. Okay. So, note that the step size that we want to choose is should actually satisfy this particular property that f of x k plus alpha k d k is less than f of x k. Okay. So, just keep this in mind. So, just some random thoughts on how to select the step size, right. What would happen if I actually choose some arbitrary alpha k? Okay. So, I understand that it has to be between 0 comma 1, like what it was given in the previous example, right. So, can I choose any arbitrary alpha which is yeah, within that particular interval, right. So, yeah, if I go out of that interval, you know that yeah, you may not get the answer, because in that case f of x k plus alpha k d k less than f of x k need not hold, right. So, as an example, let us say you have I mean let us take an even simpler example. Let us say f of r, f is a function from real line to real line, f of x is x squared, okay. And suppose I start with x equal to 2, okay. So, this is f of x, yeah. I cannot choose a very high alpha. So, yeah, in this case you can see that d is either plus 1 or minus 1, right. So, no other possibilities exist, okay. And d is plus 1 is I mean increasing the function value, and d is minus 1 is decreasing the function value. So, if x naught is 2, then d has to be minus 1, okay. And suppose I choose alpha equal to 5, okay, then x 1 is 2 plus alpha d, which is minus 3, okay. So, I go here, okay. So, yeah, I mean I am just giving you an incorrect example just to show that yeah, I mean any arbitrary alpha is not going to work, okay. So, yeah, so let us say x naught is 2, then and I choose alpha equal to 5, then x 1 becomes minus 3. So, if x 1 is minus 3, you know that d is equal to 1, that is the only descent direction, right. And if alpha equal to 7, then x 2 is minus 3 plus 7 into 1, which is 4, okay. So, you have actually come here, okay. So, you can see that you are actually going away from 0 as much as possible, because I am choosing arbitrarily large values of alpha, right. So, this certainly cannot be done, okay. So, that is a mistake, fine. So, now let us come to the question of, can I actually choose alpha which is very less, okay. So, fine, yeah, I mean I cannot choose alpha very high, because I want f of x k plus alpha k d k less than f of x k. What happens if I choose alpha to be very low, okay. I will again show you an example where it fails, okay. Let us take the same example, f of x equal to x squared, okay. And let me actually choose a very high value, let us say x naught equal to 100 for example, okay. And of course, d is equal to minus 1. I am going to choose the following values, okay. So, I am going to choose alpha naught to be half, alpha 1 to be 1 by 4, alpha 2 to be 1 by 8, and so on, alpha 3 to be 1 by 16 and so on, okay. Note that x 1 is 100 minus half, which is 99 1 by 2, and x 2 is 99 1 by 2 minus 1 by 4, which is 99 1 by 4, and x 3 is 99 1 by 4 minus 1 by 8, which is 99 1 by 8, and you can see that as limit k tends to infinity, x k actually is 99. You can see that again it is nowhere near the answer that we want, 0, right. So, what this tells us is that alpha of course cannot be arbitrarily large, which we saw from the last example, but from this example it says that alpha actually cannot be arbitrarily low as well, okay. It needs to be of the right size, is not it. So, yeah, I mean these examples are actually given to motivate the reason why the choice of alpha is very important, and the right choice as well. I mean it cannot be too high, it cannot be too low. So, you need to find the range where I mean the values of alpha that the problem can actually take, right. So, the other challenge is that how do you choose different values of alpha for different iterations, right. So, what happens if you actually choose the same value of alpha every time, okay. So, let us say I choose alpha equal to 0.5 for every possible x naught that I have, okay. So, I will again show that it fails even for this example if I choose x naught appropriately, okay. So, suppose I choose x naught equal to so yeah let us say alpha equal to 0.5. So, I will choose x naught equal to minus 0.25, okay. So, now note that I am going to choose alphas as constants, right. So, alpha 0 is 0.5, alpha 1 is 0.5, alpha 2 is 0.5 dot dot dot, okay. Now, since x naught is minus 0.25, okay. So, you can see that d is plus 1. So, x 1 is minus 0.25 plus 0.5 which is 0.25, okay. From 0.25 the d is actually negative. So, x 2 is 0.25 minus 0.5 which is actually minus 0.25, and x 3 is minus 0.25 plus 0.5 which is 0.25, right. So, what is actually happening? It keeps shuttling in between minus 0.25 and 0.25 back and forth, back and forth, back and forth, right. So, what this tells us is having a constant step size, okay, does not work, it is a very bad idea, okay, fine. So, I have given you so many examples just to show what all does not work, okay. Taking very high arbitrarily high step sizes is not working, taking arbitrarily low step sizes is not working, taking constant step sizes over all iterations is not working, okay. Now, we will try to understand what actually works, okay. So, there are two algorithms, two popular algorithms, let me put it that way, to choose the values of alpha k, okay. So, one is called as the exact line search algorithm, and the other is called as the backtracking line search algorithm, which will come a little later, okay. So, yeah, I will explain the algorithm in the first place and then say what it actually means, okay. So, let us define h of alpha as f of x naught or x k plus alpha d k, okay. So, suppose you are given the vectors x k and d k, okay, then h is actually just a function of alpha, right. So, I am just defining h as just as a function of alpha when x k and alpha k are given, x k and d k are given, sorry. Okay. So, the alpha k, the actual alpha k that you have to choose at iteration k is alpha k is the minimizer of h of alpha for alpha positive, okay. So, let me give an example of what this actually does, okay. Again we will take our usual example, f is x 1 squared plus x 2 squared and x 0 is 5 comma 4 and d 0 is minus 1 comma 1, right. So, for this what is h of alpha? H of alpha is just x 1 0 plus alpha d 0 the whole squared plus x 2 0 plus alpha d 2 0
the whole squared. So, just substitute the values, you get 5 minus alpha the whole squared plus 4 plus alpha the whole squared. We have derived this in the last class, it is 41 minus 2 alpha plus 2 alpha squared. Okay. So, for what value of alpha is this minimized? So, that can be easily found, it is h dash of alpha equal to 0 gives us minus 2 plus 4 alpha equal to 0. So, yeah, alpha is actually half, and you can also see that h double dash of half is 2. So, this is actually the minimum, right. So, what this tells us is choose alpha equal to alpha 0 equal to half. So, exact line search tells us that for this example choose alpha 0 equal to half. What does this actually mean? It means that, so we are actually looking for alpha such that f of x k plus alpha k d k less than f of x k, right. What is the best possible alpha k that you can choose given x k and d k? What is the best possible alpha k you can choose? You choose that value of alpha k for which f of x k plus alpha k d k is the minimum most, right. That is exactly what is being done here. What is h of alpha? H of alpha is given x k and d k, you are running the function over all possible values of alpha, right. And when you actually do that, you are actually seeing that, for example, if you plot h of alpha for f equal to x 1 squared plus x 2 squared x naught 5 comma 4 and d naught minus 1 comma 1, right, you will roughly get the following. So, at 0 when you put alpha equal to 0 you get 41, right. So, let me so this is a function of alpha, this is h of alpha. So, at alpha equal to 0 you have 41, okay. So, since this is 41 minus 2 alpha plus 2 alpha squared, you get something like this. Okay. So, this is roughly 1, yeah, this is alpha equal to 1 where you get 41 again. So, when you put alpha equal to 1 you get 41 again, right, and this is alpha equal to half. Okay. So, this is where h of alpha is minimized. Okay. So, that is the reason the this algorithm is actually called as exact line search algorithm, right. The search for alpha is exact, okay. There is no inexactness that comes about in this method whatever we have done here, right. So, given x k and d k, it gives you the exact value of alpha where f of x k plus alpha d k is minimized, okay. And that it I mean you can do it for every possible k, okay. So, that is the beauty of this particular algorithm, the exact line search algorithm. Now, what is the drawback of this algorithm? So, you can see that you actually have to solve an optimization problem in every iteration, is not it. So, given an x k d k, I will find an alpha using this method, right. So, you find h of alpha, put h dash of alpha equal to 0 and find the value of alpha. So, this is particular to a value of x k and d k. If you put a different value of x k and d k, you will get a different value of alpha, right. So, for each iteration you are actually having to solve an optimization problem by yourself, right. So, we came to I mean solving optimization solving an optimization problem using algorithms, because we did not want to solve for the values of x analytically, right. But here we are forced to compute the value of alpha analytically at every iteration, is not it. So, such a such an exercise can become analytically intractable very easily. Okay. I will give you an example. Let us take f r to r, and let us take this example f x minus 1 e power x minus x, okay, and let x naught be equal to 0 and d naught be equal to 1. Okay. So, let us find what is h of alpha. H of alpha is so instead of x you have to substitute x 0 plus alpha d 0. So, that is 0 plus alpha d, which is alpha minus 1 e power, instead of x again substitute 0 plus alpha, which is alpha minus alpha. Okay. So, if you want to find where this gets minimized, so you have to solve h dash of alpha equal to 0, which is alpha e power alpha equal to 1. Okay. So, if we had known the answer for this, we would not have come to solving the optimization problem at all, is not it. So, I mean it is just ridiculous that the exact line search algorithm says that I understand that you cannot solve x e power x equal to 1, but in each step you have to solve something similar like alpha e power alpha equal to 1. So, that you find the right value of alpha, right. So, I mean as I just mentioned, it is just ridiculous, is not it. So, that is actually the drawback of the exact line search algorithm. Okay. The advantage is that you get the best possible alpha at each iteration when you are given the values of x k and d k. The drawback is that it can very easily become analytically intractable. Okay. So, unless the problem is simple, okay, usually for quadratic functions. Okay. So, for example, x 1 squared plus x 2 squared is a quadratic function, right. So, in these cases exact line search can be used, but if the problem is harder, we usually do not use exact line search because it easily becomes analytically intractable. Okay. So, fine, we will move ahead to the backtracking line search. Okay. I will again first explain the algorithm before going to why we choose all this. Okay. So, note that you are actually given x k and d k, without that you do not have anything. Okay. So, other than that we also want to initialize a few more parameters. I will tell you what they are. Okay. So, the first step is initialize rho positive and C1 positive. Okay. So, I will tell you what these are. Now, we are actually running a loop while f of x k plus so you also have to initialize some alpha. So, yes, some initial value of alpha. Okay. That is also positive, of course. X k plus alpha d k minus f x k is less than C 1 alpha del f of x k transpose d k. Okay. So, while this condition is satisfied, okay, what you have to do is alpha equal to rho alpha. Okay. And so when you come out of this, you choose the final value of alpha or output the final value of alpha. Okay. So, yeah, this is basically the algorithm. Now, yeah, I suppose you at least superficially understand what is going on. So, you are actually checking some particular condition, whatever that condition means, okay, and until sorry this is greater than, okay, until that particular condition is not satisfied, right. Yeah. So, what you do is you keep reducing the value of alpha by a factor of rho. Okay. So, yeah, I think it is better written if I had changed this as rho in open 0 1 and C 1 in open 0 1. So, yeah, that is important. So, rho is a value that is strictly less than 1, it is positive, but strictly less than 1, C 1 is also positive value, but strictly less than 1. Okay. So, imagine that alpha is equal to 1 initially. Okay. What does this step alpha equal to rho alpha does? It keeps shrinking the values of alpha, right. So, for example, yeah, so let us say rho is equal to 0.9. So, in the first step, if this particular condition, whatever this condition is not satisfied, this is actually called as Armio's condition, right. So, if this condition is I mean that is if f of x plus xk plus alpha dk minus f of xk is less than or equal to C1 alpha. So, this is called as Armio's condition. Armio's condition is f of xk plus alpha dk minus f of xk is less than equals C1 alpha. Okay. So, what Armijo wanted to do is I mean choose a value of alpha such that Armijo's condition is satisfied, that is f of xk plus alpha dk minus f of xk less than or equal to C1 alpha del f of xk transpose dk, right. So, when this condition is not satisfied, so let us say I have chosen alpha equal to 1 initially. Okay. So, when I initialize the values of rho C1 and alpha, I chose alpha equal to 1 for example, okay, and I saw that the Armio's condition is not satisfied. Okay. So, what do? I shrink the value of alpha, that is it becomes alpha then becomes equal to rho, right. So, let us say if rho is 0.9 then it becomes 0.9. Okay. Then I again check for if alpha equal to 0.9 the Armio's condition is satisfied or not. So, I see that suppose it does not satisfy, then what do? I shrink it again by a factor of 0.9 which so alpha actually becomes 0.81. Okay. So, then I look at it again, I see that Armio's condition is not satisfied again. So, I shrink the value of alpha again by a factor of 0.9 because of which it becomes 0.729. Okay. So, you can keep going that way. Okay. You stop when the particular value of alpha satisfies the Armio's condition. So, yeah, that is basically what backtracking line search does. Okay. So, why is this a good algorithm? I mean at least when you just see this the condition seems very arbitrary, you do not know why someone wrote C1 alpha del fxk transpose dk and all that, right, and why should shrinking the value of alpha actually give you the right answer. I mean none of this is known clearly, right. So, we will learn all of this in the next lecture. Thank you.